So let's think about what Newton's method looks like in 2 dimensions. Remember, when we're minimizing stuff, we're really just kind of saying, here I am, which way should I go? Let me do a line search along that direction. We don't see the contours because it takes a lot of function evaluations to know where the contours are. If you're going to do contours like that, that's just going to take a lot of time. And if you did that, then you could just kind of point at where the minimum of all the contours is. So we're trying to avoid drawing the contours, but we kind of know that they're there philosophically. So I'm drawing them here just to kind of remind us what's going on. So suppose you had a nonlinear objective function, not even exactly quadratic, and here's the contours and here's the negative gradient. Think about for a sec, what will it look like? How can we diagram what's going on with two-dimensional Newton's method? And then we'll graph it. So you might copy this down and sketch what Newton's method will look like, kind of what it's doing as it does stuff here. So pause the video while you do that. Okay, and then we're going to go look at this Desmos calculator. So it's the same picture as before. So remember, Newton's method approximates the objective function using a second-order polynomial. What would a contour of a second-order polynomial that approximates the objective function at this point look like? What do contours of second-order polynomials look like in multiple dimensions? Well, if we're minimizing, hopefully they look like ellipses. So let's graph. So this is the ellipse, an ellipse of the second-order Taylor polynomial through the current point. And then Newton's method says, where's the center of that ellipse, or you could say where's the minimum of that Taylor polynomial. It'll be the center of any ellipse, any elliptical contour for that polynomial. So let's highlight that. So that's the center, and then it'll say use the direction from here to there as the search direction. It won't jump exactly there. It'll try different lengths along that direction. So it'll be kind of moving in this direction and trying to find a minimum in that direction, and then it, let's say it found a minimum about here, and then we'd say, okay, my new point is there, and let's zoom in, and remember the purple here is the Taylor polynomial, and the red is the exact contour of the true objective function, and the gradient is still leading us this way, but the Newton's method direction would lead us this way. Which looks like it's pretty close to the minimum of where that red ellipse has its minimum. Maybe the red ellipse has a minimum here. So we would search in this direction, and we'd probably end up with a minimum somewhere around there. And then we're getting the Taylor polynomial to be a pretty good approximation of the true objective function, right? Because if you zoom in enough, most functions look roughly second-order polynomial-ish in multiple dimensions. Just a quick thing I want to mention, the homework asks you to do a step of Newton's method or something. You don't have to draw elliptical contours. You can just do things kind of the way a computer does and say, here's my gradient, here's my Hessian, I'm going to do this multiplication. So you don't have to visualize them. It's actually kind of hard to draw them. You could, if you want to, go to that Desmos sheet that we were just in, because you have the link, and adapt that objective function to be the objective function that's in our homework, but you don't have to.